A constitutive equation is an equation that relates stresses to strain. And it does that through some function that depends on the material properties, in the case of geomechanics, of a rock. And for this particular function, we can choose anything that satisfies the properties of the materials. And again, that's going to depend on the type of material that we are dealing with. Often, we choose to work with linear relationships. And these linear relationships are very convenient because we can apply the superposition principle, which allow us to mix different loadings into one by using the same function or separating that function. So what I mean is that, for example, if you have an application of two strains, states A and B, by the principle of superposition, if my relationship is linear, I could write this equality that the result of applying independently these two actions or strains A and B is the same as putting those together, or is the same as applying the two actions, adding them together and applying that particular function to that. The same thing, I could say that the result of amplifying a given action with a scalar C is a result of amplifying the response of that action. And this linearity is going to be very useful because, as I was saying before, it allows me to apply the superposition principle, and this is going to be useful not only to mix impulses or actions in space, but also in time. When I have a linear relationship, I can say, for example, add up the action at time 0 and later to the action at time 1 second and say what is going to be the result of those two combined. For example, this is done when it's taken into a continuum approach to green functions. And for geomechanics, this is going to be very, very useful. But we need to keep in mind that this is only possible when we have a linear relationship between the materials. And this is going to make many things very convenient. And that's why we try always to linearize problems and to use linear relationships. All right, so what we're going to do then is to assume that we have a linear relationship between strain and stress, and this is going to be through a matrix that for now we'll just call C. And it has 4 underlying lines, and we're going to see the reason for that, but here we are relating two tensors of second order. So in order to relate those, we're going to need something which is called a tensor of fourth order. Before getting into some complicated nomenclature, just remember that this equation, it's very similar to the known I equal to B times X, where this is our independent variable and Y is our dependent variable, and this one is a constant. If we're dealing with a linear relationship, then the matrix C is going to be a constant. Okay, so let's see what this fourth order stress tensor looks like. It sounds a little bit scary, but we'll see that it's not that scary. All right, first of all, how many components do we have in the stress tensor in 3 dimensions? It's a matrix 3 by 3, therefore we have 9 components, right? And the same with the strain tensor, we have 9 components. So if we are relating 9 and 9 components, you would expect this fourth order stress tensor to have 81 independent components. Rigorously, that would be true, but we can add here one more simplification, and that's going to be that we know that although the stress tensor is a matrix 3 by 3 with 9 components, actually 6 of them are just independent. And this is the same thing with the strain tensor. So at the end of the day, in general, this fourth order tensor C is just going to have 36 components. All right, so let's see what that's going to look like. And in order to simplify writing this fourth order stress tensor, we're going to convert our matrices of the stress tensor and the strain tensor to vectors. And that's a way that we can simplify writing these equations, and that's going to be done through what is called the void notation, in which we're going to convert our tensors, like the stress tensor, from being a 3 by 3 matrix to be a 6 by 1 vector. But it is the same thing, okay? It's the same thing. It is still a tensor. It's just that we write it a little bit differently so we can actually write it, because otherwise we wouldn't be able to write this for stress tensor. And the notation that we're going to use is the one in which if the stress tensor is the usual one that we use all the time and looks like this, and remember that we just have 6 independent coefficients, so I'm not going to write the elements below the diagonal. We are going to write this as a vector following the triangle rule, in which we start at the top, go to the bottom, and go up, and then to the left. So when we do that, then this vector is going to look like sigma 1 1, sigma 2 2, sigma 3 3. I like to add a line over here to separate the normal stresses to the shear stresses. Sigma 2 3, sigma 1 3, and sigma 1 2. Pay attention that sometimes some people, or in some other communities, they use a different notation, and they may start in this position, in the fourth position, with sigma 1 2. So just keep an eye on that. We're going to use this notation that I just wrote. All right, so let's write now the stress vector and the strain vector, and let's see what has to be in between in order to hold the relationship between stress and strain. All right, so let me go ahead, and since I wrote this already, let me just copy it and paste it. This is going to be my stress tensor written as a vector. Here I'm going to have my matrix that links strain and stress, and here I will have my strain vector that looks the same, follows the same rule as the previous one. And here for the strains it's going to look a little bit differently, because we're going to see that by convention we're going to need to use a 2 over here, but this is just a convention, and we'll see the reason for that later on. All right, so I have a 6 by 1 vector here, I have a 6 by 1 vector here. I'm going to add these lines that help divide the normal from the shear stresses. What you would expect to have here is a matrix of 6 by 6 by inference. And we're going to denote this matrix with the elements following the same convention that we use for the stress tensors and in general to matrices, where the matrix C is going to be populated by C11, C12, C13, and so on in the first row. And when you continue with the different rows, then it's going to look C21 and so on. I'm not going to write everything, okay, but I guess you get more or less what you should expect. For example, here is going to be C61, C62, and so on. And this one is going to be C66. And these are going to be our 36 independent coefficients. Notice that if I have a stress over here and this is a strain, these C values are going to have the unit of stress in order to have dimensionality in this equation. So this one is going to be called and let me use a color to highlight that this name. This is going to be what is called the stiffness matrix. In general, that relates the stress tensor to the strain tensor. All right, so let's see how we can now simplify a little bit this stiffness matrix into something more meaningful and more practical that we can use in mechanics. All right, so let me just copy all of this and I'm going to paste it over here. The first thing that we're going to do is we're going to apply what is called the shear decoupling principle. The shear decoupling principle states that normal stresses cannot produce a shear strain. So, as a result of that, normal versus shear, there is not going to be a possibility of normal stresses causing a shear strain or a shear strain causing a normal stress. Probably you can picture this in your mind, but you know, just imagine for a moment that if you were to apply just a compression on one direction or even in all directions, there is no reason for thinking that that would distort the shape of an element. And we're going to see an exception of that in a little bit, but in general, this is going to be the rule that is going to tell me that, for example, these shear strains over here, epsilon 23, epsilon 13, epsilon 12, they cannot cause any stress or normal stress, sigma 11, sigma 22, and sigma 33. And as a result of that, in order to enforce that condition, that means that when I multiply a row times a column, these elements over here have to be 0. And let me use a color coding for this because it's going to be useful in order to understand that what I mean over here. And that was for sigma 11. For sigma 22 is going to be the same. All those shear strains over here cannot cause any normal stress. And I could also think on a similar thing for these other normal or linear strains over here. These linear strains cannot cause a shear stress. Therefore, these elements here are going to be 0 as well. And there is going to be another shear decoupling second application, which is when you relate shear to shear. And in this case, what the shear decoupling principle is going to state is that a shear in a given plane, for example, in the plane 2-3 or strain in a plane 2-3, cannot apply a shear stress or cannot result in a shear stress in the perpendicular planes like 1-3 or like 1-2. So let me just draw some of those planes so it's a little bit clearer. So if I have a cube like this one and I have a shear distortion in this plane, that cannot be caused by a shear stress which is in another plane. And because of that, then now these elements are going to be zero. This one, that one, this one, and that one. Let me just complete the matrix. This is C22, C23, C31, C32, C33, C44, C55, and C66. So now I have, it looks like we have 9 plus 3, 12 coefficients, right? But actually we do not have 12 coefficients because this matrix, because the stress tensor is symmetric and the strain tensor is symmetric, this matrix is also going to be symmetric. So instead of 12 coefficients that you see over here, 12 independent coefficients, we're going to have actually 9 independent coefficients. And these 9 independent coefficients are going to be able to fully define what is known as the orthorhombic geometry or the orthorhombic symmetry. And let me make a schematic about this. So now with 9 independent coefficients, I have the orthorhombic symmetry or an orthorhombic model in which, for example, if I were to have a coordinate system like the one that we have been using, north, east, and down, and I have a rock here which is composed by a block. In this particular block, if C11, C22, and C33 are different, that's going to mean that they have a stiffness which is different in all directions. For example, I could have a stiffness which is different in vertical direction than in horizontal direction. This is usually the result in sedimentary rocks caused by layering and piling up geological layers with different properties. But just the fact of sedimentation, and this is very strong, for example, in shales, adds an isotropy to the rock. So now it's not the same to apply a stress in the vertical direction than in stress in horizontal direction. But in addition to that, I could have a stress in horizontal direction which is different depending on which horizontal direction I take. For example, I could have fractures, vertical fractures that are in direction north-south that break this block and add a compliance to it with now this set of fractures, so that when I compress in direction east-west, it's not the same as if I were to compress it in direction north-south. And in order to make it more general, let's just add a second set of fractures. I could have now a fracture set which is perpendicular to this and probably is even thicker, with fractures which are thicker and more compressible, so that now I also have a different stiffness depending on the orientation in which I apply stress. The anisotropy in the shear coefficients is a little bit more difficult to see, but I let that on your own to investigate and to try to picture in your mind, and just keep the case for the normal stiffnesses. And what we're saying in this case, for example, is that if you were to measure the Young modulus in the vertical direction, that's going to be different than the Young modulus in the horizontal direction, in direction north-south, and that's also going to be different than the Young modulus in horizontal direction, in direction east-west. And this is what is called an orthorhombic material. All right, let's simplify this a little bit, and let's get rid of the fractures, and let's see what we would get in that case. Let me copy my block, and hopefully I can get rid of those fractures without deleting other things. Let me try that. Okay, so I'm getting rid of the compliance now of the fractures, and now the stiffness is going to be the same in the horizontal direction, in the two directions, but it's going to be different in than in the vertical direction. This is what is called a vertical transverse isotropic material, or vertical transverse isotropy. Let's just keep it like that. So remember, the first one was orthorhombic, this one is vertical transverse isotropy. And in this case, we have, for example, for this particular example, that I have a rock with layers aligned in horizontal direction. Then usually happens that when we have this type of combinations, I would have layers of stiff and soft rock, and when you use the volume average properties, and something we're going to do later on when we get in detail to talk about this, we usually find that the vertical Young modulus is smaller than the horizontal Young modulus. And also this model, it is called sometimes also axis symmetric, because if I were, for example, to put this an axis over here, and in this case would be, by analogy, this would be the third axis, it looks the same. All the material looks the same around this axis. All right, so with the vertical transverse isotropy now, let's see what the matrix is going to look like. So we say that for the orthorhombic material, we're going to have 9 independent coefficients. For vertical transverse isotropy, now the what happened there? For vertical transverse isotropy, I'm going to get rid of, but actually not get rid of, but let me try one more time. Okay, I have to reorganize this a little bit. Some of these coefficients are going to be now the same. Let me fix this first, and then we'll go through that. So here's 2 epsilon, 1 3 2 3 actually 2 epsilon, now 1 3 2 epsilon 1 2. And because now the stiffness in the horizontal direction is the same, what I'm going to do is I'm going to see how that affects the matrix. Before we do that, and in order to continue with the same notation as the one that we have over here, remember that this particular system, it's based and it's defined so that the north is the first element, the east is the second element, and direction down is the third element. So sigma 1 1 will be the one going in direction of the north, sigma 2 2 in direction of the east, and sigma 3 3 in the vertical direction. All right, now since the horizontal directions, the stiffness in the horizontal directions are the same, then C11 is going to be equal to C22, and we're just going to call it C11. And because of that too, the shear stiffnesses are also going to be the same in a particular direction. So if I were to apply a shear stress in the plane 1 3, you would expect that that's going to be the same as applying a shear strain in the plane 2 3, because that's applying stress in the same, it's basically the same plane. It's just that it's at 90 degrees, but because this is axis symmetric or vertical transverse isotropic, it's going to be the same. It's not going to be the same than in the plane 1 2. Notice that that one is different. So this one is going to be different than the other ones, but C44 is going to be equal to C55. And because of that, now I have different, we have less independent coefficients, and let's just count those. C11, that's 1, C33, C12, C13, C23, and C44, and C66. Let me see if I am counting here correctly. No, yes, I'm counting correctly. Another term that is going to be the same, I almost forget about that. It's, imagine that you push in direction 3, right? If you push in direction 3, what you would expect is that the response or the expansion that you will get in direction 2 and 1 are going to be the same. And what that means is that, for example, if I take it to this particular case, sigma 3 3, if I were to again apply and stress in direction 3, because of the Poisson effect, the expansions in direction 1 and 2 should be the same. And because of that, these elements, these two, have to be the same, because these two expansions that I expect here are the same. And because of that, and by symmetry, this one I know is C13 just by symmetry of the matrix, and because of the property that we said about transverse isotropy, this one is also going to be C13, and this one is going to be, now again by symmetry, C13. And since we're here, also let me change this one also by symmetry to C12. And now I have, let me count again, C11, C33, C12, C13, C44, and C66. Similarly to what happens with the relationship between the shear modulus and the Young modulus, you can actually show that C66 is a function of the other stiffnesses, and it's equal to what I'm writing right now. So at the end of the day, I just have 5 independent coefficients, and that's the VTI model. If you want to use the VTI model, then you're just going to need to measure 5 independent coefficients that we'll see later on how to do that. All right, so notice that we have gone from a very complex case, which is the orthorhombic case, to the vertical transverse isotropic case. And before we had 9 independent coefficients, now we have 5 independent coefficients. We're just gonna go one more level of simplicity, and we're going to make this cube to have the same properties in all directions. And this is simply called isotropy. And remember that we're talking about linear elasticity, so this is linear elastic isotropy. And when this is the case, it doesn't matter what is the direction in which you apply the stresses, the rock deforms the same. If you apply in vertical direction, or in direction east-west, or in direction north-south, the properties are going to be the same. And we're going to further define the variables that characterize the relationship between stress and strain in this case. All right, so let's get started. I'm losing a little bit of energy here, but I'm sure I can make it. All right, what we're going to do is, again, here we're going to define, this is going to be the first axis, the second, and the third. This is just easier to do the notation I'm going to use. And I'm going to apply a stress here in direction 3. I'm just drawing one arrow, but keep in mind that this is in stress, so it's applied evenly everywhere in this solid. All right, when I apply this stress, I would have another stress that comes from the other direction, and I would expect a shortening in direction 3, right? So if I were to draw the deformed configuration, it would look something like what I'm going to draw right now. Again, it shortens in direction 3, and it expands in direction 1 and 2. All right, in red, then we're going to have the deformed configuration. And let's try to quantify that deformation. Originally, this element, and here we're going to apply the kinematic equations, had a length in direction 3 dx3. When it deforms, here it's deforming on the two sides, and the total amount of deformation or displacement is du3, but is the same on the top and the bottom. And also, this one is going to expand in direction 1 and 2. In this case, let's just plot what is going to be the displacement in direction 2. This is divided by 2 because I'm going to have the same thing over here. And now with these definitions, I think that we are ready to define the elastic properties. Okay. As we saw before, the strain in direction 3 is equal to the change of length divided the original length. The strain in direction 2, the linear strain, is the change of length in direction 2 divided the initial length in direction 2, which in this case, I forgot to add that one, is dx2. And epsilon 11 is, I'm not drawing that in the schematic, but it's going to be similar to what we had over here for the deformation in direction 2. All right, now that I have applied an stress and without any confinement from the sides or without applying any other displacement or stress on the sides, this is freely deforming in direction 1 and 2, I can define the Young modulus. And the Young modulus, by definition, I have seen this notation recently in a book that I like it very much. It's an equality, but it's an equality enforced by definition, is equal to the stress divided by the strain that causes that stress in the same direction. And this is the Young modulus. And remember, it's a definition. And now I have characterized the relationship between stress and deformation in the same direction. What about in the transversal direction? That's going to be taken care of by the definition of the Poisson ratio, where the Poisson ratio is, by definition again, equal to the ratio of the strain transversal to the application of the stress divided the strain in the direction of the application of the stress. And I have a negative sign here because these strains are going to be, one is going to be a contraction and one is going to be an expansion. For example, for this particular case, epsilon 33 is going to be a contraction, epsilon 11 is going to be an expansion. Those are going to have different signs. So when we define the Poisson ratio, we use the negative term because we're taking into account that most materials are going to expand when you apply a stress in a transversal direction. And because this solid is isotropic, I can do the same thing for the other transversal direction, epsilon 22 related to epsilon 33. And this is what is called the Poisson's ratio. Okay, so let's see now what we do with these definitions and how they help us to get back to where we wanted, which is this stiffness matrix. Okay, so what we're going to do then is just to write what are the resultant strains from the application of a given stress with what we have drawn over here. And I like to keep this in the picture, so let me just zoom out a little bit. And let's say that I have a stress tensor which is 0, 0, sigma 3, 3, and no shear stresses. And this is going to result in strains, which are, as I'm seeing over here and applying the definitions that I have used, epsilon 3, 3, I get it from here, is going to be equal to sigma 3, 3 divided the Young modulus. The shear strains are going to be 0, I hope you notice this from the diagram, but I'm applying normal stress that doesn't cause any shear strain. But now, epsilon 1 and epsilon 2, I'm going to have to apply the Poisson ratio definition. All right, so in order to do that, epsilon 1, which is going to be located here, then it's going to be the Poisson ratio times negative epsilon 3, but epsilon 3, I know is sigma 3 divided the Young modulus, right? So then epsilon 1 is going to be equal to negative Poisson ratio divided, I need some space over here. Let me zoom in again to be able to write that in the space I have. So this is going to be Poisson ratio divided Young modulus times sigma 3. And it's going to be the same thing with epsilon 2. So now I see that my strains are just a function of sigma 3. And I can use now this analogy, and instead of just working with sigma 3, I could also expand the same thing and following the same procedure to what would happen if I apply an stress sigma 2, and what would happen if I apply an stress sigma 1. And the result is going to be the following. In general, epsilon 1, epsilon 2, epsilon 3. Let me not write the shear strains for now. It's going to depend on this matrix. And it's going to depend on the stress tensor, written, remember, as a vector. And following the same principle that we did before and looking at what the result should be, and notice that if I want to write now this equation and put this sigma 3 is the one which is right here. So if I wanted to multiply or obtain the coefficients that will result in such equation for epsilon 1, epsilon 2, and epsilon 3, I would have to, for epsilon 1, the element that I would need would be the 1, 2, the third element, because the third element of the row is the one that is going to multiply to the third element of the column. So this one is going to be Poisson ratio divided Young modulus, because it's what we have over here. For the second one, it's the same. And for the third one, when I have coinciding the strain and the stress direction, I have positive 1 over E. If I do that now for sigma 2 is very similar. The strains caused by stress sigma 2 in direction 2, the linear strain would be inversely proportional to the Young modulus, and to the sides I would have these proportionality coefficients with the Poisson ratio and the Young modulus, and for 1 is going to be analogous, and I will have the following. All right, we are almost halfway of finishing this matrix. We know from the previous analysis that all of these are 0. That's, if you remember, it's called the shear decoupling principle, relating normal and shear stresses or strains. We also know that these are 0 because of the shear decoupling between the shear and shear in different planes. And finally, here, if I add now the shear strains, I have not shown the solution for this in this video, but I'm going to show the solution and the derivation of why this is true in another video, in which I'm going to post a link later on so you can access to that. But I just want to keep it simple in this case. This is going to be linked through the shear modulus. By definition, this is a G, where the shear modulus is equal to, and again you can show that, I'm going to do it in a different video, is a function of the Young modulus and the Poisson ratio. So at the end of the day, look where we have got. We have a relationship between strain and stress, and the matrix that links these two is what is called a compliance matrix. Notice that it has the units of 1 over stress or 1 over pressure, compliance with N. This is the compliance matrix. And this compliance matrix has just 2 independent coefficients in the case of linear isotropic elasticity, which are the Young modulus and the Poisson ratio. All right, last thing. We started with a relationship that was actually trying to calculate stresses as a function of strains, not strains as a function of stresses. So if I want to do that, what I should do is multiply the inverse of this matrix to the left of the strain. Actually, I'm missing here 2 lines. And if I do that, then I would be able to recover what I've been looking for, which is the stiffness matrix. All right, so this one is going to result in the identity matrix, and this one, the inverse of the compliance matrix, is going to be the stiffness matrix. So if I move now stress to the left, this is the stiffness matrix, and this is the strain tensor, where these two things are the same, and they are the stiffness matrix. And you can try inverting this matrix in Wolfram alpha. It's not such a nice and enjoyable work to do it by hand, but you will find out that when you take the inverse, the solution is going to be the following. Stresses as a function of strains and sigma 1,3, sigma 1,2. In order to save some writing, I'm going to take a common factor, which is this one, and inside my stiffness matrix, this is going to be equal to here 1 minus Poisson ratio. It's actually a relatively simple matrix. And these are all the same. And remember, these are zeros. This is 0, this is 0, and here we have the strain. Okay, so we are done. So now this is the stiffness matrix that we have found from the definition of the Young modulus and the Poisson ratio, and allows me to link stress and strain for the linear elastic isotropic solid. We're going to see later on how we relate and how we find this stiffness matrix, especially for the case of the vertical transverse isotropic model, because that's a model which is very relevant to rocks. And later, when we talk about plasticity, also we're going to see that sometimes the shear decoupling rule does not apply for plasticity, and we're going to see some exceptions where a shear strain can actually cause a normal stress or a normal strain. But for now, we're just gonna keep it here.